look at your calendar. Hold on, I'm looking at it in my head. A1, A2. I think corrections will be due on Monday. I think there's a homework due on Friday, if I remember right. I'll double check tomorrow. But some of you should be able to get through these corrections super fast, super quickly. So I would say get this out of your life as quickly as possible, but we won't get the calendar today. Okay. We're recording. Here we go. Chapter 8, Section 1. I'm seeing if my iPad will work. Right now, he's not very happy. All right. Matrices. Question, cool kids. What are the 4 ways that we've solved systems up until this point?
Elimination.
Elimination, substitution, anything else?
Row
echelon form? Elimination, substitution, row echelon form? Oh, Gauss? Gaussian elimination? Gaussian elimination?
Oh, those elimination.
Yeah, I think that's what I'm thinking about. I would say letter A should be substitution. That's kind of the earliest method. Letter B should be elimination. I'm trying to delete notes to see if I can free up space. I don't know what's going on. I'd say A is substitution. I would say B is elimination. C, I would say, is row echelon form. And D is going to be matrices. However, row echelon form leads into matrices, which will be nice. We could put graphing. That's probably technically the other review idea. We could put graphing. It's not my favorite. We'll just end with matrices. But graphing, I just need you guys to remember, is definitely a valid technique. When we graph, how do we find solutions with graphs, cool kids? Intersection points. Good. How do we find solutions with graphs one more time is intersection points. Now, matrices, a rectangular array of real numbers. Huh? A rectangular array of real numbers. Let me get a pen. Today's going to move rather slowly, and I apologize for that. I want you guys to write ANN. A matrix is some sort of compilement of entries shown by ANN. Technically, I guess we could theoretically put this over here with entries. The matrix is not just one element, but it is instead comprised of elements. Entries are the individual little letters, and the individual little letters, let me get back to my pen here. They can be different sizes, as we all know. Remember we talked about matrices right before last test, you guys could double check, etc. The very first entry is always denoted A11. It could be A00, but we don't usually use that with matrices. So A11. What would the next one be? Is it 1, 2 or 2, 1?
I don't know. I'm going 1, 2. 1, 2.
How can we tell? Go ahead and grab out your graphing calculators. We're going to have to get here eventually anyway. I'm going to point out that I realize that a lot of this you can be cheating on. But we are going to learn how to do it by hand as well. So I'm going to show you stuff in your calculator, but sometimes it's easier to do by hand, and sometimes we need to make sure we can do it by hand no matter what. This test will definitely be part calculator, part non-calculator. Just as a heads up. If you go to matrix, that's second something, right? Exactly. Second x to the negative 1 or x reciprocal. Let me get out of here because I'm on some weird graphing screen. Okay. Even just to put in a matrix to your calculator, don't you have to think about which number is which one comes first and which one comes second? Right? If you do a 1 by 1, how big is that matrix?
One number.
It's one little number. Why? One row, one column. when I go up and do 1 by 2 instead? Is that 2 rows or 2 columns? We'll check it out. What is it? 2 columns, 1 row. So the very first number goes or associates with rows. The second number associates with columns. So if we were to instead go ahead and make this like a 2 by 3, for instance, we should see how many rows and how many columns? If I make it a 2 by 3, how many rows? 2 and how many columns? Perfect. And that's what we see, right? So coming on back, A11 would be first row, first column, the entry therein. A12 would be the first row, second column, the entry therein. And then can't I kind of just do a dot, dot, dot to say, keep going? What's going to be the first element, or the second element, I should say, down? What's that one going to be denoted? A21. Good. For second row, first column. And we can keep on going. A22, A23, etc., etc., etc. And we were just talking about order, and the order is the number of, if I were you, I'd label it just to make sure you remember, but you do have your graphing calculator as a backup in case you forget. M stands for how many what? Rows. And N stands for how many columns. Okay, so ready, set, go. Find me the order of each of these matrices. There should be 2 numbers separated by a multiplication sign that is not a multiplication sign. Instead, it represents the word by, like a 2 by 4. 8.5 by 11. 11 by 17. What you guys get on A? Yep, 1 by 1. How about B? 1 by 4. How about C? Hey, he also has what solely as his entries? Hey, he's called zero matrix. That's cool. Letter D. Alright, so we're good on order? You have to remember which way it goes, but otherwise it's pretty simple, yeah? Let's keep talking about the basics of matrices in the next page. A row matrix is solely comprised of 1 row. A column matrix solely comprised of 1 column. A square matrix solely square matrix. Who goes inside that? Then an identity matrix. I'll give you a second to go ahead and get down our key terms. Hopefully my iPad is loading the notes. You guys figured out why this bottom one is called square matrix? Exactly. So square matrix would be a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4. Let's just call it an M, representing however many rows by. Does that make sense? It'll be an N by N. Whereas the column matrix will be n by 1. Wait, is that right? Which one goes first, rows or columns? Rows go first. Oh, did I put an n? Oh, that's annoying. Hold on. I switched the terminology. You guys didn't get super confused by that. We know n stands for a number, right? Is that okay? N by 1, however many rows you have by one singular column, whereas a row matrix will be 1 by n. I apologize, I wrote it backwards on the page before. That's okay. One row, m elements, m columns, whereas this one is one column, n rows. And the identity matrix is just a special name for any matrix that is a square matrix number 1 and number 2 has a leading diagonal. That's what this one's called, from left to right. The main diagonal, leading diagonal of 1s, and the rest of the entries are all 0s.
What's the third one? Your synthetic division.
I'm trying to think of why it does.
Oh yeah, it was just check.
Maybe that's why. I can't think of another reason off the top of my head. Unless you're like setting up with the zeros, setting up the coefficients or something. But... Alright, are we almost there? For the good and the bad, but for right now, the good. I'm catching up, cool kids. I'm catching up. What order did we say solving the system? Substitution was first, right? Then we said elimination. Then we said row echelon form. You guys are wondering what I'm doing. I'm getting caught up real fast. Wow. We'll speed it. How do you guys spell echelon? Spell it right. Yeah. What else do we have? Entries we said were what? Hey, we're reviewing what we just covered. That's what you guys should be doing every day. Anyway, entries. What did we put down for that?
That was just the A.
You start with A11 and we talked about how you go A12 and keep on going, or A21 and keep on going, right? Keep on going, however much you want to go. Order we talked about. What comes first again? Rows, and what comes second? Nice. Order. 1 by 1, then what? Then what? Then what? Nice. Look at you guys. Square matrix, we talked about how, once again, it's n by n. Column matrix is an n by 1. Row matrix is a 1 by n. Identity matrix, leading diagonal of 1s, the rest of them are 0s. Something spiffy about an identity matrix that we'll talk about soon. Any matrix A times the identity equals the identity times A equals A. The identity times a matrix, or a matrix times the identity, I should say, is itself. And that kind of comes back to the additive identity and the multiplicative identity. Like, let's see, what's the additive identity? 0, right? What's any number plus 0? Itself. The multiplicative identity is 1, because any number times 1 is itself. The identity matrix is the multiplicative identity, in that any matrix times the identity matrix is itself. Okay. Now it starts to get spiffy, because now we start talking about augmented matrices, and augmented matrices put together, with a little separation dotted line, put together the coefficients from a system of equations, the coefficients from the system of equations. The coefficients, or that square matrix, is augmented with, some of you guys have heard of augmentation. The coefficients are augmented with, for lack of a better term, we'll just say the solution column. Maybe it might be a little bit better to say coefficients, aka coefficients of variables with the constant column. Because technically that's what's going on. We have x, y's, and z's, and then we have the constants, right? We have the variables with the constants. So we separate a system of equations into coefficients with variables and then the constants that they go together to make. What's really important, just like with any system, it's really important to line up the x's and the y's and the z's so that each, in the matrix, each column is representative of separate variables, and each row is indicative of different constraints, leading back to our linear programming section 7.6 thing above. Each row is a different equation. There's a different relationship between or among the variables. Each column is a different variable itself. And the nice thing is we're going to use, basically, in our matrices by hand to solve the exact same system that you learned back last chapter with row echelon form and the stair step. And this is where the programming comes in as to how your calculator can do it as well. But remember, we actually talked about last chapter how there are some systems, some infinitely many solutions, consistent but infinite, that your calculator would just say error or would just kind of freak out and not give you a nice pretty solution. But you need to know how to interpret, and if you know how to solve by hand, you will be able to interpret what the solution is. Row echelon form in context of a matrix is going to be, and there might be some more information on this later in notes, but long story short, it's going to be a leading diagonal of ones. First characteristic that has to be true, leading diagonal of ones. The second characteristic that has to be true is the bottom half of the leading diagonal splits the matrix into the bottom half of zeros. If you're able to get it into row echelon form, leading diagonal of ones, bottom half of zeros, then you will still need back substitution to solve. You'll still need to remember the stair step from the last chapter. There is a further simplification called reduced row echelon form. In your calculators under the matrix math, there's REF, which is row echelon form, and RREF, reduced row echelon form. But we'll get there in a little bit. So row echelon form, leading diagonal of ones, just like we did leading coefficient of ones with the stair step last chapter. Zeros all below, but you can have constants up above. You guys see me zoom in the bottom middle? Now guys, every problem where we are working with the matrix and trying to use it to solve using matrix math, everyone is a new problem to tackle. Everyone is a new challenge. Everyone is going to take time and careful mental math. Please don't see this section as just like Miss D trying to make our lives awful and not letting us use our calculators. But instead, we're working on mental math. We're working on systematic thinking. We're working on introducing further application of math called linear algebra. The math isn't necessarily hard, but the mistakes are so easy to make. All right, are we close?
What does the last thing say?
Oh.
Zeros?
Leading diagonal of 1s and bottom half of 0s. Leading diagonal of 1s, bottom half of 0s. Leading diagonal of 1s, bottom half of 0s. Okay. Woo! This is the system that you just wrote. So you don't have to rewrite the entire thing. You already wrote the system up above in your examples. You already have the augmented matrix. How do we get this augmented matrix in row echelon form? Well, we kind of do what we did last chapter, but shorter and just with numbers without having to write all the x's, y's, and z's. Matrices are a shorthand of basically solving systems of equations. So we start with the original augmented matrix. And just to make my life and your lives a little bit easier as we go through this example, I'm just going to focus in on the augmented matrix. We know it comes from a system, and hopefully we can write a system as an augmented matrix and vice versa. But for right now, I like to write these over to the far left, kind of like you would in a homework paper. My augmented matrix is 1, negative 4, 3, 5, standing for 1x minus 4y plus 3z is equal to 5. Negative 1, 3, negative 1, negative 3, standing for negative x plus 3y minus z is equal to negative 3. My third row is 2, 0, negative 4, 6, standing for 2x minus 4z is equal to 6. Now, if this was written with equations, like you guys can see up above, if it was written with equations, what would our system, our row echelon system, where would it take us? What would we do? Yeah, we would take the first two and say, hey, we gotta get you guys to match, right? Link the first two, link the second two, and we go from there. We're gonna basically do the same thing here, except with matrices, we have to be very, very careful about the system that we approach. And we want to establish 1s along this leading diagonal. Now, we don't have all 1s, right? But we do have 1, 1. If there was another equation that had a 1, we would move it into the first spot. We have a 1 already established. That's the first look whenever we're doing a matrix. Now our job is to get this second one established. So the system is a little bit different. However, what we could do in moving forward, in matrices we use little arrows to show going from one step to the next, is we could go ahead and do something like, ready? We could do something like row 1 plus row 2. But we have to go ahead and do, or tell ourselves where to put it and say put it in row 2. Now remember, rows, that goes across, right? What am I doing when I do row 1 plus row 2? I'm going to eliminate, because 1 plus negative 1 is going to be a 0. So I'm going to add all the row 1 entries with all the row 2 entries, the corresponding ones, and put the answer in row 2, meaning I'm not going to change row 1. He's fine the way he is. I have 1, I have negative 4, I have 3, I have 5. I like him because he has a leading coefficient of 1 in the right spot. But when I go ahead and zoom in, or when I go ahead and look at row 1 plus row 2, kiddos, what's 1 plus negative 1? 0. What's negative 4 plus 3? What's 3 plus negative 1? What's 5 plus negative 3? Why did I like that, or why did I want that? Because I have a 0 below, which is what I want. I want a leading coefficient of 1. I want zeros below. I'm ultimately, hopefully, going to get zeros all there. Oh, except I'm going to have leading 1s. So let me show you once again where we're trying to get. Row echelon form, we're trying to get a leading diagonal of 1s. We can have numbers up top. We don't really care. But we want zeros in the rest of the spots, and then we hopefully have some sort of A, B, and C off to the side. Okay? So I got a 0 below.
Should you flip
Flip
the
what?
signs in the second one?
Yeah, I can flip the signs. So I'm going to go ahead and rewrite. 2, 0, negative 4, 6, because we did not change row 3 in any way, shape, or form. That one stays the same. Now Luca's like, hey, wait a minute, you want that leading coefficient of 1, so let's just change this negative 1 to be what?
1.
But we have to show our math. We're going to go ahead and say, okay, we're going to do negative row 2 into row 2. If you're doing programming, you're going to do a step, and then you have to tell the step where to output. So that's kind of what this is symbolizing or showing. Row 1, I haven't touched, he's staying the same. Row 3, I haven't touched, he's staying the same. So what just happened to all the elements or all the entries in row 2? They all get flipped, yeah. So what is 0 times negative 1? Oh, he stays the same. What's negative 1 times negative 1? What's 2 times negative 1? And what's 2 times negative 1? We're just working with numbers. We're ignoring the x's and y's and z's, just working with the numbers. So we have our leading coefficients. Wait a minute, everyone's kind of getting to be good, except who's this little guy that I've kind of forgotten about? That's good, that's good. Oh, who's not? That 2's not good, right? So what can I do with row 3 to get rid of the 2?
Honestly, you could divide them by 2 because you have 2, negative 4, and 6.
Yeah, but if I divide
Or
by
negative
2,
2 and 3.
I need a 0 though, that'll get me a 1. Right? We need a bottom of zeros. If I make it a 1, that's true, I can make it row 1, row 3, but couldn't we do row 1, row 3 right now? Couldn't we get row 1 to match row 3 so we can cancel out? Yeah, so let's multiply row 1 by negative 2 and let's add it to row 3. Putting that in row 3. It's basically elimination. The 1 and the 2 need to match and be opposite in order to add and have them cancel, right? It's basically elimination. It's like numerical elimination. This is where the math gets a little hard and the mental math gets a little hard to store away. I'm not changing row 1, I'm not changing row 2, not in the matrix. I like them the way they are, but I am changing row 3, but how? Yeah, each time, each entry. What's 1 times negative 2?
Negative 2.
Plus 2?
0.
0. Right? What's negative 4? Plugged in. What's negative 4 times negative 2? 8. What's 8 plus 0?
3.
What's negative 2 times 3? Negative 6. Negative 6 plus negative 4? Negative 10. What's negative 2 times 5? Negative 10. Negative 10 plus 6? Negative 4. Are we in row echelon form? Ugh. No. But we're closer. And some of you are like, no, you're not. We just lost the 0 in the second part. Yeah, we did. But we have a very solid first column that's going to stay with us no matter what we do. How are we going to get rid of, here's a hint on matrices, we work by columns. The first column is established, he's done. The second column, I love the 1, I hate the 8. The negative 4 is fine. How do I get rid of that 8 now? Yeah, go find the 1. Go find the 1 and say, hey, if I do negative 8 times row 2 plus row 3, that's going to make that 8 into a 0. The established ones are kind of like our little reference points in order to use to eliminate whoever we need. So they multiply each entry one at a time. If I multiply to 0 by negative 8, what do I get? 0. And 0 plus 0 is? 0. We can go ahead and rewrite our row 1 and our row 3. Sorry, our row 1 and row 2. because we're not changing him. He's fine. If I multiply 1 by negative 8 plus 8, there's our 0. If we multiply negative 2 by negative 8, 16 minus 10, 6. And if we multiply our negative 2 by negative 8, positive 16, minus 4. Whew. Our first column's good, our second column's good. Now all we need to do is make our third column good. Yeah, can't we just divide, not by 2. We want to make this one into a 1 to make our leading coefficient match. So how do we make 6 into 1? We do 1/6 row 3 into row 3. 1, negative 4, 3, and 5. 0, 1, negative 2, negative 2, 0, 0. 1/6 of 6 is 1. 1/6 of 12 is 2. Whew! Did I finally get this thing into row echelon form? Yes. The dilemma with row echelon form, though, is that number 1, it doesn't look like your calculator's identity matrices that it tries to get, in that these ones aren't 0 yet. So it's only kind of half done. However, kiddos, right now we can go ahead and go backwards and say, wait a minute, this one tells me z equals 2. This one tells me y minus 2z is equal to negative 2. This one tells me x minus 4y plus 3z is equal to 5. Hey, what do I have? A stair step. How can I solve it? Back substitute, back substitute, back substitute. Solve, solve, solve. Alright, kiddos, way to hang in there. You got an introduction of matrix math. We'll play around with this more tomorrow. We're not done. That's why homework's not due until Thursday. I would work on corrections tonight.